Hi Edgar. Right, basically the first point, though, that bullet point on the specification is essentially just graph transformations. So if you know how to sketch a cubic, you're good, mate. But the next question about points of inflection and stationary points, I'll do a little example and talk you through what's going on. So when we have a stationary point, the definition of that, so if we've got stationary point, that means that the gradient is equal to 0. Okay, now that essentially means that there is no change in the y coordinate as you change the x coordinate. Yeah, so that rate of change of the y compared to x is 0. It's very easy to see those points. That would be, if you drew a tangent to the graph, I mean, oh, my notability is going crazy there, but if I drew a line there, I would get a stationary point. Yeah. So this here is going to be a stationary point, and we can just see from the graph that that is actually a maximum. I'll talk a bit more about how we can prove that that's a maximum in a minute. Here we've got a minimum, and again that's got a gradient of 0. So essentially we differentiate it, and we want to find where that gradient is equal to 0. Now, a point of inflection, that happens when the graph changes from being concave to convex, or the other way around. Right, and the way that we measure whether a graph is concave or convex is by looking at how the gradient is changing. And that means we've got to look at that second derivative. This is a measurement of how quickly the gradient is changing. When that is 0, that's when we get a point of inflection. Okay. Now, if we look at some of the things that are going on here, the point of inflection, I can kind of just eyeball them, and I'll show you why I can eyeball them. Well, there's definitely one there, because I can see how the gradient is changing. Okay, and what's going to happen if I just talk you through this. At this point of the graph, the gradient is really positive, it's very steep, and as I travel along this graph, it becomes less steep. Okay, until we get to that point which is 0. So in this section of the graph, that means the gradient, the change in the gradient, it's decreasing. So that means that this value here would give us something that's negative. It continues to decrease because after we've gone past 0, I then get a negative gradient, and it becomes more and more negative until I get to somewhere around here where it actually then starts to increase. It becomes less and less negative until it comes to 0. Okay, so that in that middle section of the graph, something really interesting is happening. It's almost like if you were on a slide. You'd feel yourself speeding up, and then there'd be a bit in the middle where you kind of catch yourself and then you slow down again. All right, and that measure, that feeling of what's happening would be you'd accelerate in that section and then decelerate as you come towards like the lip or the bottom bit of the slide. Now in that section, that means that the graph must have a positive change in the gradient. And actually, if we continue that on, it just becomes more and more and more positive as we go. Okay, so it would continue in that section of the graph. So if I highlight these bits, this section of the graph, until I get to somewhere around there, we'll calculate it in a minute, that's going to have this property where the gradient is decreasing. Okay. Now the name for that is that is concave. And that's how we can actually find a maximum point, is that if you found this position here and you found the first derivative, if you then differentiated it again, we'd see that that section of the graph would have this concavity. It would have a concave relationship with that maximum. So that's how we can show that that's a local maximum. And the opposite thing happens. So we get a different colour. Let's go green. In this section of the graph here, we've got that this is convex. And that's, again, if I found the point where that local minimum is, I could then substitute it into my second derivative and I'd see that I get something positive, and that would be a local minimum. So final bit, we actually want to find where that point of inflection is. I said it looks roughly around there, like by eye, but let's go on and actually find it. So we've got the equation of a graph here. I'm going to differentiate it. So we get 3x squared minus x minus 2. And I think we can, let's just very quickly factorise that. We don't need to because we're finding the point of inflection. But just to show you that when we make those equal to 0, we do get the 2 points on the graph. I get negative 2/3 or x is equal to 1. And that's my local max and my local min. Let's go again then. So differentiate it again. Cool. So we're going to get 6x minus 1. And then we're going to set that equal to 0. And that gives me 1/6. There we go. Oh God, that is bad. Whoa. Set that equal to 0. Whoa. And then solve it. So we get x equals to 1/6. And if we zoom in, that kind of makes sense to me. Because my guess, can you see I was maybe just a bit closer to that one? A 1/6 would be about there. Yeah, so I think with hindsight, I'd say, look, there we go. We've got that value of 1/6 is my x for my point of inflection. That is not to say that points of inflection are always halfway between stationary points. They don't have to be. And you can have stationary points that are also points of inflection. They just have to have both of these properties at the same time. And the simplest example I can think of is if you had y equals x cubed. If we differentiate that, we get 3x squared. That means that at x equals 0, we're going to have a stationary point. And then if we differentiate it again, we get 6x, and again that would be x equals 0, we get a point of inflection. Okay. That doesn't happen for x squared, because when you do the second derivative you get 2, which means that if it's always 2, the whole graph is convex and you get a local minimum. Alright, so I hope that's helpful. Basically those points of inflection, you're doing a very similar thing, but you've got to differentiate twice. And it's that change between it being concave to convex is what we're looking for. Right. Right, I hope that helps anyway. And yeah, keep them coming if you have any more questions.